Hey, what's up? It's Miss Wesley. This is our final day of binomial distribution practice, and I'm looking at statistics packet page 17 for starters. We're backtracking and actually going to add a little throwback. I don't know if it's a Thursday, but we have a throwback for you today. We're going to start with number 16 where it says expand. Joke to get you started. Well, I would tell you guys a steak joke, but they're never well done. Why would I put this on this page? Take a look at 16. It says expand the binomial. Let's decide as a group that we do not want to write out x plus y 5 times and FOIL it with itself that many times. I mean, maybe it would be fun, but I highly doubt it and it would take way too long. So if you'll recall, let's do this how we used to do it. We had a shortcut for it. Good old French mathematician philosopher Pascal came up with a triangle where each row started and ended with some ones, and we could add the diagonals to get the next number in the spot we need, right? There's no need to memorize the numbers in this triangle as long as we can add, like a 3 and a 3 is going to make a 6 there. And let me get myself all the way down a couple more rows. 1, 5, 10, 10, 5, 1. Let's put a row 6. 1, 6, 15, 20, 15, 6, 1. And just for the fun of it, let's add this row because I'm going to use this as an example. Not only was it fun, in my humble opinion, to make this triangle, it was useful because it gave us a quick way to find the coefficients of this binomial expansion. If we want to find the coefficients when x plus y is raised to the fifth, let me go straight to the row that has a 5 as its second number and space out these coefficients. So 1, a 5, a 10, and then 10, 5, 1. And there was a nice, easy to follow pattern with the x's and the y's. The x's started to the highest power in our shortcut, so x to the fifth power, right? And then we'll count down by ones. So x to the fourth, if you can squeeze that in there, x to the third, x squared, x to the first, and then no x left over for that last term. And the y's kind of did the opposite. There was y to the 0 in the first term that I'm going to completely leave out. Y to the first, y to the second, y to the third, y to the fourth, and y to the fifth. Now, aside from some ones that I left in here that I can definitely take out to keep it more simplified, this is it for the expansion. This is pretty much what it should look like. And what was cool about it was it didn't take us that long to get it. The coefficients were nicely located in Pascal's triangle, so that was kind of cool. And the exponents are always going to add up to 5. So if I get to the middle here and I know x is squared, I could think, oh, y is going to be to the third because that would add up to 5. And that was a good way to do things. Now, I've hinted at this before, but we've never formalized it in our notes. What's the point of bringing up this triangle other than I like it so much and it's kind of fun and there's the cool patterns in it? Why bring up the triangle now in the midst of a packet about probability and statistics? Do you see any probability or statistics in the triangle? Because you should. There are combinations hiding in this triangle. So I'm just going to say here, Pascal's triangle contains combination values. And I don't know if we formally recognize this together or if we haven't yet. Take row 5, for instance. How many ways are there to choose one thing or 0 things out of 5? There's one way to pick no things out of 5. 5C0 is going to be 1. There are 5 ways to pick one thing out of 5. 5C1, try it on the calculator, equals 5. How many ways are there to pick 2 things out of 5? There are 10 ways. 5C2 is going to equal 10. 5C3 is 10 again. 5C4 is going to be 5 again, and 5C5 gives you 1. Same thing for the 4s. Here's 4C1, 0. I got to start with 0. 4C1, 4C2, 4C3, and 4C4. So the combinations are here, and there's a version of the binomial theorem that could have come into play when we were first learning tricks for expanding binomials, but now it should make some more sense, either using Pascal's triangle coefficients or thinking of the coefficients just as combinations. If I want to raise a plus b, let's say to the 6th power, you would start with 6c0, right? The first number in that row of Pascal's triangle as a coefficient. 6c1, 6c2, all the way up until you get to 6C5. You're almost done, and 6C6 is going to be your last coefficient. So those are your Pascal's triangles numbers, and they're also going to be combination values. And then the A's and the B's followed the same pattern that they always did. This binomial theorem is not only a good way to expand binomials, it's a good way to jump to a specific term of a binomial expansion if you need it very quickly. So for 17, I mean, this really is a review question, and there's no reason that you can't go back to using Pascal's triangle, but another way to think about 3x minus y to the fourth is to think about combinations that have to do with 4s. So start with 4C0. Think of how many ways you can pick no things out of 4, and there's just one way that could happen. You pick none. Then 3x, according to the exponent pattern, is going to be to the fourth power. We'll put it in careful parentheses. Next coefficient is going to be 4C1. You're just traveling up till you get to 4. 3x will be to the third, and a negative y will be to the first power in that term. So how many ways, and this is 3x to the fourth, so this is 1 times 81, x to the fourth, like that. If I'm going to the second term, just trying to simplify as I go, how many ways are there to pick one thing out of 4? There are 4 ways. You could choose one of each of the 4 things. Then you've got 3x to the third, so 27x cubed, times a negative y. This whole term will come out negative. We got a few terms to go. So 4C2 is going to be the next coefficient. 3x squared would follow the pattern, and then negative y would also be squared. Instead of simultaneously simplifying, let me just put the last 3 terms on here. So the next coefficient will be what? Use a combination, 4C3. Then 3x to the first power, negative y to the third power. Just keeping going with that pattern. Last term, 4C4. I know I've hit the last term because I've gotten to the final possible combination. 3x is to the 0 power, so I'm just going to get rid of it in this term, and negative y is to the fourth. So then what's left to simplify? How many ways are there to choose 2 things out of 4? You can type this into your calculator, you can use the formula, or you can just use Pascal's triangle. The next coefficient is going to be a 6, and then you have 9x squared times y squared, because that negative will get canceled by being raised to an even power. What's 4C3? If you check it, it's going to be 4 again. And it's no coincidence that these 2 are the same value. The number of ways to choose one thing out of 4 is the same as the number of ways to leave out one thing out of 4, 4C3 and 4C1. The symmetry is going to match up. So times 3x times negative y to the third. And lastly, how many ways are there to pick all 4 things out of 4? There's only one way to do that. Times, I'll just put regular y to the fourth because a negative, again, to an even power will turn out positive. Last simplification. I like the first term, 81x to the fourth. Second term has to get multiplied. 4 times 27, so minus 108. X to the third, y. And then plus 54, x squared, y squared. Minus, how about 12, xy to the third, and plus y to the fourth. And we've got that expansion. It's a good topic to return to because I love this algebraic shortcut for when we need to expand binomials in the future. And also, it's kind of nice to see. I mean, there were so many patterns in Pascal's triangle, and here's another one, all the combinations. And speaking of the 7s, I want to use this row 7 to go ahead and try to do number 18. 18 doesn't say that you have to expand the binomial. It just says you have to get the third term. So we got to count in. I mean, look at the 7th row. It's a 1, 7, what was it, a 21, 35, 35, 21, 7, 1. There are 8 total terms in this expansion if I count those 8 coefficients. Here's the first one, the second one, the third one is going to have a coefficient of 21. So the third term is always going to be, it's actually sitting right here, it'll be NC2, 1 lower than 3. So it'll be 7C2 times 2x to what power? Well, the formula says do 7 minus 2, make it to the 5th power. We can also confirm this by counting in. This will have 2x to the 7th, the 6th, the 5th power for that third term. And then what is the b2? The second part of it is just to the 2, so the negative 3y should just be squared. If I'm going from patterns, negative 3y would be to the 0, the 1, and the 2 for the very third term. So we've gone over how this is 21. This simplified is 32x to the 5th. And this will turn out being positive, right? Positive 9y squared. So it is a bit to multiply, and I would grab a calculator to help, but at least I didn't have to really write out the entire expansion to get the answer to this particular question. So you should get, you can check me on this one, about 6048 x to the fifth and y to the second, just to get to the third term. You'll see some good practice with this and other, just binomial distribution review moving forward with the examples that I'm going to direct you to. If I just flip over to the next page, we could help solidify this on page 18 with this lesson check, questions 3 and 4. Notice both of these, neither of them have you actually expand out the binomial. Instead, it's directing you to a specific term again. Can we find the fourth term if we were expanding c plus d to the sixth? The fourth term, according to the binomial theorem, the fourth term should have the first coefficient 6c, and then afterwards we'll say 3, right? We'll do, if you're counting into the fourth term, right, I go to that row of Pascal's triangle. It's a 1, 6, I think 15, 20. So first term is 6c0, 6c1, 6c2, 6c3 goes there. So 1 less than 4. Next up, the c. What power will it be raised to? Well, it'll be raised to c to the sixth, fifth, fourth, third, c to the third power. Next up is the d. The d has to have an exponent that adds up to 6. So since a 3 is already there, another 3 is going to happen. This will be 6 minus 3, which gives you the third power. So try that. 6c3 is going to be 20, and then c to the third, d to the third should be your fourth term. How about the next one? The second term of this binomial expanded. So x minus 2y to the fifth power. Try it from the theorem. So it's 5c. We want the second term. So 1 less than 2 would be 5c1. First term coefficient would be 5c0. Second term would be 5c1. What power would x be raised to? Well, it's only the second term. So we're counting 2 terms in. The fifth, the fourth. 5 minus 1 gives you the fourth. And then negative 2y has to be raised to the power that we can add to 4 to get 5. That should just be to the first power. So 5c1, don't need to type that in, can do it by common sense. How many ways are there to choose one thing from 5? Is just going to be 5 ways. Times x to the fourth times negative 2y to the first power. How about we make this a negative 10x to the fourth y as the second term. And you see some other good review problems here in this lesson check. I just want to talk about one more, number 6, just to refresh it. It's been a few days since we've talked about the actual definition of a binomial experiment. 6 says explain. Go ahead and explain how flipping a coin 10 times meets all the conditions for a binomial experiment. These problems where we've been using the binom PDF and binom CDF shortcuts in our calculator. Well, do we remember them? What are the conditions for something being binomial? I'm just going to type the answer at the bottom here in this space. You have repeated trials. You're flipping a coin 10 times. That's what that is. Each trial has 2 possible outcomes. You either flip a coin and get heads, or you're going to get tails. That's why they call it binomial, because one of 2 things could be occurring. The probability of success stays the same no matter what. We'll say is constant throughout the trials. You have a 50-50 chance. Probability of heads, let's say, success is going to be 0.5. And this also infers that the trials are all independent of one another. So get to practicing. It was my pleasure, and I'm excited to go over some more of this stuff with you soon, and I'll talk to you later. Have a great day.